In this video, let's see how we may use Simplex algorithm to solve a linear programming problem, and then we see how we may identify that the problem itself is actually unbounded. So just a reminder that there are four possibilities when we solve an LP model. We may have a unique solution, what we've seen in the week 4, and then alternative solution that we have seen in the previous video, and unbounded LP model that we are going to talk about in this video, and then infeasible LP model that we will see later. So let's see an example in which the LP problem is actually unbounded. Okay, so in this example, Bread Co. Bakeries bakes two kinds of bread, French and sourdough. And then they can be sold for 36 cents and 30 cents. So it must be talking about something related to the objective function. When you see the require something, it talks about the constraint. Same here, it talks about the availability. Bread Co. has 5 yeast packets and 10 ounces of flour at present. So it's still about the constraint. And then here it says additional yeast package can be purchased at 3 cents each and additional flour at 4 cents per ounce. So here, because it is talking about you can buy something more, but it costs you something, then it must be about the objective function as well. Because it says finally that you want to maximize bread cost profits, revenues from selling the breads, and costs from buying additional packets of yeast and flour. So starting from the objective, we say that revenue, we get it from selling French bread and sourdough. So let's say 36x1 French bread and then 30x2 sourdough. And then the costs come from buying additional yeast packets and then additional flour. So additional yeast packets, we can say it is x3, additional ounce of flour is x4, such that this is our objective function, revenue minus cost. Now this is the specific definition for each decision variable. X1 is the number of loaves of French bread baked. X2 is the number of loaves of sourdough bread baked. X3 is the number of yeast packets that we purchased, and then X4 is the number of ounces of flour purchased. Remember that when you define decision variable, they must be as specific as possible. Now let me give you a pause on the video to give you time to read all the information and understand the decision variables and objective function. Now we have two constraints here in this problem. The first constraint is related to the yeast packages, and the second one is related to the ounces of flour. Of course, it makes sense that when you make this bread, the yeast packages that you use cannot exceed what you have on hand, plus the additional packets that you purchase. Same with flour, what you use to produce the bread cannot exceed the flour that you have on hand, plus the additional flour that you purchase, right? So let's talk about the yeast. So for each French bread, you require 1 packet of yeast, and then for the sourdough, you also need 1 packet of yeast. It cannot exceed 5 packets that you have on hand, plus x3, which is the additional number of yeast packets that you purchased. For the flour, it's the same, 6 ounces for French bread, 5 ounces for sourdough, cannot exceed 10 ounces that you have, plus additional ounces of flour that you purchased. If you move all the variables to the left-hand side, the constraints will look like this. So to complete the formulation, do not forget to add the sign restrictions saying that all variables must be non-negative. Okay, now let's solve the LP model using Simplex algorithm. So first you need to convert the LP model into a standard form, but I don't show it here. I go directly to the table. I hope by now you're already familiar with reading this table, so you can see that actually this is how the standard form is represented in the table. We have S1 slack 1 for the first constraint, S2 or slack 2 for the second constraint, because both constraints have the sign of less than or equal to. So in this table, you see that we have BFS because the table is in a canonical form 1, 0, 0, 0, 1, 0, and 0, 0, 1. So it's in a canonical form. We have basic variables which are all positive. So this is a BFS. For the maximization problem, this table is not optimal because you can see in row 0, you still have variables with negative sign. So we go to step 4 and say that x1 should be the entering variable because it has the most negative coefficient in row 0. And then you perform ratio test and pick the smallest one as the winner. So now it means that S2 becomes the leaving variable. So x1 is the entering variable, S2 is the leaving variable, and the pivot is located here in the intersection. So this is what we had from the previous slide. Now in step 5 of the simplex algorithm, you perform arrow or elementary row operation such that the column of x1 will look like this. So the column of x1 will become 0, 0, 1. The only position where it is 1 is where the pivot was. And other position, it becomes 0. So you perform arrows and then you get the new BFS here, the second table, the second BFS, and then you check again for the maximization problem. This is still not optimal, such that you can say x4 should become the entering variable, and then the leaving variable is S1. The pivot position is here. Now you do arrow again such that the column of x4 becomes 0, 1, 0. The only position where it is 1 is where the pivot was. Now you reach the last table and you say that for maximization problem, this is still not optimal because the coefficient of x3 in row 0 is negative 9. So this is not optimal for a maximization case. However, when you try to perform ratio test, the ratio test for all constraints, for all equations, the result is none. So this is the sign that your problem is unbounded. You have an entering variable, but the ratio test is none, which means that no variable should leave the basic variable. You don't have a leaving variable. Or in other words, you may enter the variable that you want, in this case x3, with the value as large as possible. That's why the problem is called unbounded. Now let's take a closer look at the unboundedness of this problem. So we will ignore all the non-basic variables because the value is 0 and we don't have any intention to change them. So we will ignore x2, s1, and s2. We only consider the basic variables at this moment, x1 and x4, and x3 is the entering variable that we try to enter to the basic variable. So we only consider x1, x3, and x4. Let's write down the equation based on this table. So in the row 0, you have z minus 9x3 equals 100, right? And then I just move x3 to the other side, so we have z equals 100 plus 9x3. And then in this row, we can write this down as minus 6x3 plus x4 equals 20. But then I move minus 6x3 to the other side, so it becomes plus 6x3. So the last constraint or last equation, we can write it down. x1 equals, x1 minus x3 equals 5, but then I move minus x3 to the other side, such that now it becomes plus x3. So these three equations is simply I rewrite what is represented on the table. So because the ratio test is negative, it means that you can set the value of x3 as large as possible. So when you set x3 any positive number, regardless of how large it is, x4 and x1, they will still be positive. So those who are in the basic variable at this moment, they will still be positive. They will not violate the sign restrictions. So that's why this problem is unbounded. You can set the entering variable with the value as large as possible without causing the variable that are in the basic variable at this moment to become negative. They will still be positive, so you can set x3 as large as you want. So for example, if you want to set x3 such that the z value becomes 1000, so notice that the current z value is 100. If you want to increase z to becomes 1000, what should you do? Well, you just plug in z equals 1000 and z from this table equals 100 plus x3. So you know that x3 must equals 100. So it means that you increase x3 from 0 to 100 and it will make your z becomes 1000. Okay, so in this case, you can set x3 equals 100 to reach z value equals 1000. But as I've said before, because this problem is unbounded, you can set x3 as large as you want and you get z as large as you want, and then the problem is still okay. By okay, I mean that the basic variables x4 and x1, they will still be positive. So that's why this problem is an unbounded problem. So you may wonder why that example may become unbounded. Well, there are several possibilities. For example, first, the demand is assumed to be unlimited. You may produce as many breads as you want and people will buy it. That's the assumption in that example. Also, the second possibility is that we ignore the capacity of the resources, like the ovens, the labors, and so on. There's nothing about this in that example. Also, we may buy unlimited quantities of additional packets of yeast and additional ounces of flour. So again, this all mean that you may produce as many breads as you want and people will just buy all the breads that you have. If that's the case, then it's very good, right? If you have a bread or a bakery, it means that you just keep producing as many breads as you want and then you get unlimited revenue, right? But that usually is not the case in the real world problem. So when you have an unbounded problem, usually something is missing in your model. Okay, now let me check your understanding with a question. So given a maximization case and then given a BFS, and then this is the statement. The ratio test results are none for all constraints. So the result is none for all constraints. It means that we can't increase x3, while x3 is currently equals 0 because it is a non-basic variable. Is this statement true or false? I will give you the answer after the pause on the video. Well, the answer for this problem is false. In fact, we can increase x3 indefinitely. So the ratio test none for all constraint. It means that for the entering variable x3, you may set the value as large as possible, as positive large number as you want. And that's why this problem is called unbounded. So that's the end of this video. In the next video, we are going to talk about another special case, which is called degeneracy. So see you in the next video. Thank you.